Okay, let's discuss a little bit about the Dirac Delta function as a singular distribution. I already show you that we define the Dirac Delta function as t of delta applied to phi equal to phi at 0, where phi is our test function. Or we can even use the notation using the scalar product delta comma phi equal phi at 0. We need to be careful because now what we have here is just a symbol, is not anymore a regular function, okay? But we can still keep the notation in this way. Now, the natural definition of the derivative, we know that formally the derivative of delta prime comma phi is equal to minus delta comma phi prime. This by definition of derivative. Derivative of a distribution. We prove these results, we prove this relation when here we have a regular distribution, we have a regular function which is locally integrable, and then we use this relation as a general definition of a derivative of a distribution. If this is true, now we relate the distribution of delta prime to delta. Now we know what is this delta. This delta, what is the action of delta on a test function? It returns me the value of the test function at 0. So from this, I can say that this is equal to minus phi prime at 0. And that's that we have here the definition of the derivative of a delta function, which is equal to minus phi prime at 0. And that's what we already know, is right? That's how it's usually defined. But now you see at least where does it come from. And now you also know that when you take the derivative of a step function, this is basically the delta function, right? That's what people have been telling you in classes, right? Let's try to see what is the meaning of this relation in the sense of the distribution, because now we know how to take the derivative of a distribution. So let's consider the u dt comma phi. If we apply the definition of the derivative, or we can even do the integration by parts, we know that this is formally equal, I'm going to redo the steps, integral minus infinity to infinity of the u dt times 15 delta t. When you do integration by parts, you take the antiderivative of this guy, which is basically u of t, times phi t, between minus infinity and infinity, minus the integral between minus infinity and infinity of ut times phi prime of t and delta t. But because the test function phi is defined on a compact support, this term disappears, is 0. So we have that the u dt comma phi is equal to minus u comma phi prime, or we can call it the phi dt, just to keep the notation. But now we know what is the action of the test function of the regular distribution of u, because this is what? This is equal to minus the integral between minus infinity and infinity of ut the phi t in delta t. And this is equal to minus integral between 0 and infinity of the phi t in delta t. Is right? Because we know that this guy is equal to 1 only between 0 and infinity. But now I can solve this integral very easy. It's an easy solution because the antiderivative of this integral is the test function itself. So I have a phi t between 0 and infinity. Now phi is defined on a compact support. So the value at infinity, we have this is equal to, minus phi at infinity minus phi at 0. And now phi at infinity is 0 because phi t is non-zero only on a compact support. And at the end we end up with plus phi of 0. So what do we have here? Very nice results. And so we start with the derivative and we end up with these results. So the derivative of the u dt as a distribution is equal to plus phi at 0. But we know what is this distribution. This is a distribution of a delta by definition. So we prove that the distribution of the u dt is basically a distribution of delta. And so we can associate to this distribution the function the u dt equal delta t. And that's how that's how you can prove in a rigorous way that the derivative of the u dt is basically equal to delta. Okay? So let's see other properties of the delta function. For example, if I want to compute, you know that f of t times delta t, what it does when you do this product. You have a generic function, and then here you have a delta at t equals 0. This operation is equal to f0 times delta t. That's what, this is the localization property of delta. Localization property of delta t, of delta. Let's try to prove it using distributions. We start with what? Distribution of f times delta comma phi. And again, I have to do, the distribution associated with this function is this. I use the dot product with a test function. Now here I have a product of a regular function and a singular function, okay? And we know that I can take the regular function and bring it on the side of the test functions. Formally, this is equal to delta comma f times phi. And I can do that, okay? I can only bring the regular one on the other side, okay? Not the delta. And this is well defined because I have a regular function with a singular one. If I have the product of two deltas, it cannot be done, okay? It's not defined at all. But now I know what is this distribution. This distribution is equal to the value of f times phi computed at t equals 0, which is equal to what? F of 0 times phi 0. So we show that, we have that phi delta times phi is equal to f of 0 times phi of 0. But now I know what is this distribution. This distribution is what? It is delta comma phi, is the distribution of a delta. So we have that f times delta phi is equal to f at 0 times delta comma phi. And these results, which is valid in the sense of distribution and makes sense in the sense of distribution, can be associated to this to functions. And so I have the product of a function f times delta is equal to f at 0 times delta t. What I wrote here is just a symbol which represents this distribution. Okay? And now, since we already talked also about delta primes, and if I do f of t times delta prime of t, what I get? Would be this equal to, you know, by looking at this property, it would be natural to say, oh yes, this is equal to f of 0 times delta prime of t. Nope. Unfortunately, no, this intuitive reasoning doesn't work. And so distribution are a really strange object. So there is an extra term here. Besides this, we need to also add, the final formula is f0 times delta prime t minus f prime at 0 times delta t. So that is the true, the correct equality. So there is an extra term, and that's very weird, right? So let's see if we can derive it using using distributions, okay? Because we know how to manipulate the product of a regular function and a singular function. This is well defined in the sense of distributions. So let's do that. And so we want to show we have this f of t times delta prime of t. In the sense of distributions, this is basically f times delta prime comma phi. Again, I have regular distributions times a singular distribution. So I can bring the regular distribution on the side of the test function, as I show you in the previous lectures. This is a property. This is delta prime comma f phi. But now, because I know that this is a test function, okay, that's why I can do that. But now I know what is the definition of delta prime. This is equal to minus the derivative of the test function f of phi applied at t equals 0. This derivative is equal to minus f prime times phi plus f times phi prime at t equals 0, or minus f prime at 0 times phi at 0 plus f at 0 times minus f at 0 phi prime at 0. Now I know what is this. This is actually, let me write this as minus f prime of 0 phi at 0 plus f of 0, which multiply minus phi prime at 0. So we know what is distribution. This is delta comma phi. But we know also what is the distribution. This is delta prime comma phi. So we show that this is equal to minus f of 0 delta comma phi plus f of 0 times delta prime of phi. So what do we show basically? We show that f delta prime comma phi is equal to f of 0 delta prime comma phi minus f prime of 0 delta comma phi. That's what we show. But this is equivalent to f delta prime equal to f0 delta prime of t minus f0 times delta t. Okay? And this is they are important properties that you should remember, because they will allow you to do calculations of derivatives using singular functions. And in this end the lecture.